Welcome to the latest episode of the MFG Radio Network's Lunch and Learn, as we highlight some of the latest advances in manufacturing and design, gain insights about the newest products and technologies to move your manufacturing ahead of the competition.
Hello, everyone, and welcome to our Manufacturing Lunch and Learn. I'm Elizabeth Engler-Modick, Editorial Director of GIE Media's Manufacturing Group of Magazines, and I will be your moderator. This session looks at surface analysis, the key to enhancing manufacturing efficiency and quality. Surface analysis provides insights into the composition, structure, and properties of surfaces and interfaces that directly affect product quality and performance. Presenting on this topic is Ashley Maloney, PhD, a senior staff scientist with physical electronics. As a staff scientist, Ashley provides technical expertise to physical electronics in support of new product and application development while demonstrating its system's performance capabilities. So, without further ado, Ashley?
Thank you very much, and thank you for that introduction. Again, I'm from Physical Electronics. My name is Ashley Maloney, and today I will be talking about surface analysis, the key to enhancing manufacturing efficiency and quality. I'm aware that surface analysis may be a little bit different from some of the manufacturing talks that some of this audience has heard previously. So I want to spend a little bit of time here talking about what surface analysis is and how it's important and how it could help you solve some of your manufacturing problems or contribute to developing better products. So again, I'm from Physical Electronics. We make surface analysis equipment, and you can see pictures here of the three main products that we make. In addition to manufacturing these products, we also provide contract analytical services for customers interested in just getting data from our instruments and not purchasing one themselves. So to get started, I will talk about what is surface chemistry, what is surface analysis, and why is surface chemistry important. So I have a few examples here of what surfaces are. Surfaces are where of course, corrosion or rust happens. Surfaces are also where adhesion takes place or doesn't take place. Surfaces are also where catalysis occurs as the gas interacts with the solid surface in order for catalysis to operate. Of course, that's a surface interaction. Surfaces are also where mechanical parts become lubricated. Surfaces are where medical devices contact the body. Surfaces are where electrical contacts are made, where the rubber meets the road, so tribology, the study of wear and tear. Surfaces are where thin layers form. Glass, of course, is made of many thin layers, and paint as well, coatings and thin layers. Thin layers form on surfaces. Surfaces are where semiconductor devices operate. It's where sunlight contacts solar panels, and finally, where charge moves around in batteries. So all of these examples are examples of important surfaces where surface chemistry is critically important to the performance of the materials and the devices. So hopefully based on this, I have convinced you that surface chemistry is important, and surface analysis is also important in looking at device performance. So how does surface analysis work? How is it performed? We have three different techniques, and all of our techniques, we have an analytical probe that will interact with the surface, and that will cause a signal to come out of the surface. So all three of our techniques have a different probe that probes the surface, and they get a little bit different signal that comes out of the surface. And they all have their pros and cons, and I'll talk a little bit more about them throughout this presentation. So analytical probes have different penetration depths. We have three different probes that we use. We use photons that has a penetration depth of about 1,000 nanometers down into the sample surface. We use an electron source as a probe with a penetration depth of about 2 nanometers. And we use an ion probe with a penetration depth of about 1 nanometer. So to maintain surface sensitivity, if we want our signal to be coming only from that top surface of the sample in order to analyze the surface chemistry, we must get a signal out that is characteristic of just the surface. So we want to look at either electrons or ions coming off of the sample surface to use that as our signal. Here's a little bit more information about our techniques. You can see in this diagram here on the left, I have circled in black our analytical techniques compared to some other common ones such as EDS, SEM, that you all might be a little bit familiar with. So in this diagram, we have the detection range plotted on the y-axis and the spot size on the x-axis. So for example, in Auger electron spectroscopy, one of our techniques, we have a very small spot size down to about 10 nanometers in analytical spot size. And we have a detection limit of around 0.1 to 1 atomic percent. XPS, X-ray photoelectron spectroscopy, is another one of our techniques. For this technique, we have a little bit bigger spot size being about 10 microns, and the detection limit being similar to Auger, about 0.1 to 1 atomic percent. And then last, we have time of flight secondary ion mass spectrometry. We can see that its real advantage here is that it has a very low detection limit in the parts per billion range, and the spot size can get as small as less than 100 nanometers for our instruments. Here is a table summarizing our three techniques. The real advantage of AES is that we can get very high spatial resolution. We can get about 8 nanometer spatial resolution. The information that we get from Auger is mostly elemental, and in some cases we can get chemical state information. XPS, another one of our techniques, we have a bigger spot size, so larger spatial resolution. The real advantage of XPS is that we can get short-range chemical information. And then finally, TOF-SIMS, we can get about 70 nanometer spatial resolution, get very low detection limit, and we can get molecular information. So throughout this presentation, I'll talk a little bit more about each technique. And then at the end, I will give some examples of how we've used these techniques to help solve manufacturing problems. Here's just a quick snapshot of what the data looks like coming from our instruments. So XPS and HAXPS can give you elemental information and chemical state information. This is an example of an XPS map that was collected on a bond pad. So we can see the optical image. We have a gold bond pad, and this is the corresponding XPS image where we can see calcium in red and gold in green. So we can actually map out the distribution of elements on the surface. TOF-SIMS is another one of our techniques, and where it really excels is that it can actually show you molecular information. So this is the ion image that we collect from a TOF-SIMS instrument, and you can see that the colors correspond to red being CH. So the TOF-SIMS, the really distinguishing thing here is we can get molecular information as well as elemental information, and we can look at those in an ion image. And then finally, this is an example of some of the data that you could collect on Auger. Auger really excels in high spatial resolution. So these are some features in the electron image, secondary electron image, and then the corresponding Auger image where you can get spatial resolution down to about 8 nanometers. And we can see there is no shadowing on these highly topographic features. So here's a little bit more detail about XPS and HAXPS. So XPS is X-ray photoelectron spectroscopy, and HAXPS is hard X-ray photoelectron spectroscopy. And like I mentioned before, it can provide valuable quantitative and chemical state information from surfaces. Our instruments have the ability to get lateral spatial resolution of about 5 microns for XPS and about 14 microns for the hard X-ray source. I will quickly go over this diagram of how XPS works. We shoot the sample with an X-ray photon that will excite a core level electron from the sample surface, and the emitted photoelectron is characteristic of the atom from which it came. So we are detecting the binding energy of core shell electrons. And the binding energy, like I said, is characteristic of the atom that it came from. It also corresponds to the chemical state of the atom. So the binding energy of carbon will have a slightly different binding energy if it is bonded to oxygen versus hydrogen or another carbon. And you can tell those chemical state differences in the spectrum for XPS. TOF-SIMS is our second technique that I'll discuss. And like I mentioned, it is good for imaging the distribution of elements and molecules. So really the distinguishing thing here with TOF-SIMS is we can image molecules. And this is good for organics, plastics, polymers, things that have large molecules we can see and detect in TOF-SIMS. And this next slide shows an example of the type of data you could expect to see from TOF-SIMS. The way it works is we would hit the sample with a primary ion beam, and then we would detect the secondary ions coming off of the surface. So we would get an ion image of all the ions that are coming off of the surface, and each pixel here represents a full mass spectrum. So what that means is we can look at the mass spectra, and we can look at one specific species in the mass spectrum and pull out a chemical information or a chemical map from that ion. So in this example, we would see this is the total area spectrum. And if we wanted to look at where this peak is on the surface, we can map just that peak. And same for this one down here. We can get different spatial distributions based on the molecules that are present in the mass spectrum. And then finally, we have Auger electron spectroscopy, and where it really excels is high spatial resolution. So it is quantitative. We can get elemental and in some cases chemical state information from Auger. And really the distinguishing thing here is it can get a lateral spatial resolution down to about 8 nanometers. The way Auger works is if we have a primary electron beam, and if it has sufficient kinetic energy, it will bombard the atom and lead to the ejection of a core shell electron. And so the energy of this ionized atom is reduced by an electron falling down into the initial hole from a less tightly bound state. And that leads to the ejection of a second electron that is emitted from the atom. And that is the Auger electron, and it's characteristic of the atom that it came from. So every element has a different kinetic energy for the Auger electron. And so it's this Auger electron we are detecting, and that tells us the atom that we're looking at. So now I will discuss a few specific examples of the techniques and how they can be used in the manufacturing process. So first I will talk about microelectronics applications. How can we use surface analysis to help solve some microelectronics failures? So in this first case, we have an electronic door lock that you would use on your front door with a keypad that would automatically unlock it. We had an example of a keypad that was no longer functioning. We removed the battery case and we saw 2 contacts, this one here positioned between A and B on the sample holder, and this one here positioned between F and G on the sample holder. And we can see just optically that the 2 contacts look very different. This would be the good contact that has silver and relatively uniform in appearance, while this bad contact over here is discolored, has kind of a yellow discoloration and some patchiness to it. So in this case, we decided to use XPS to analyze the differences between these 2 contacts. So first we started with the good contact, and in this we can see this is a mosaic map of the X-ray induced secondary electron image. So all of these images are snapshots of the sample over a large area, and we stitched all those individual snapshots together to form this larger image over the whole contact pad. And then we did XPS analysis on just this blue area here. And we can see in the XPS spectrum that on the good contact, we have about 80% nickel, and then we also have some carbon, oxygen, and nitrogen. We can also see a little bit of sodium due to sample handling. But the takeaway here is XPS has shown us that nickel is the primary element on the surface of the good contact. To compare, we looked at the XPS analysis of the bad contact. And again, we took a large area image, and then we collected XPS from just this spot here in red. And on the bad contact, we can now see oxygen and zinc and copper, as well as potassium. So we have a bad contact that appears to no longer have the nickel plating, which serves as a protection layer. So it may not have been applied during production, or the presence of potassium here indicates that this bad contact might have corroded due to the alkaline battery. So this is an example of how XPS is used to look at some failures on surfaces of, in this case, an electronic door lock. And we can now help the customer track down in the manufacturing process why this failure has occurred now that we understand the chemistry. We can also use Auger electron spectroscopy to look at microelectronic defects. So here we have, we have an SEM image of a defect. So this kind of structure here, the customer was wanting to analyze and figure out the chemistry of what's causing this defect. So in our Auger electron spectrometer instrument, we have a focused ion beam to create in situ cross sections. So what we've done here is we can see the feature in the SEM image because this has been cross-sectioned first in the fib. And then we can look at that freshly exposed fib face with Auger, and we can get corresponding Auger maps. So we can see titanium nitride in red, aluminum in green, and tungsten in blue. So we can see the chemical structure of this defect that we were observing in the SEM image. It's important to note here that the scale bar here is 1 micron. So the features we're seeing in the Auger image are nanometer scale features. So this really highlights the high spatial resolution mapping capabilities of Auger. My second example here was a problem that a customer was seeing with wire bonding. So they had these wire bond failures that were on these pads that we see in the optical image here. So we had a sample with some bad contact pads and a sample with some good contact pads, and we used XPS to look at the differences between the good and bad. So here are the results of the XPS analysis on the good pad versus the bad pad. So this is the optical image of the two pads, and these crosshairs here represent the analysis areas. So we dropped points right on the pads and looked at the XPS spectra from the points that we dropped. On the good bond pads, we can see relatively low amounts of fluorine compared to the bad bond pads where we see very high amounts of fluorine. So because we have a small spot size in XPS, we can drop it just on the pads and get chemistry from the pads. And we can see differences in the fluorine signal in good versus bad. We did this across 6 different pads. So here we can see 6 good pads and 6 bad pads and the fluorine concentration between the two. Obviously, the good pads had about 2 or 3% atomic percent fluorine compared to the bad pads that had 10 or 11 atomic percent fluorine. So fluorine appears to catalyze growth of a thicker aluminum oxide layer that can interfere with wire bonding. So they were seeing poor wire bonding on these bad pads due to the high fluorine content. Additional analysis, they were able to trace the source of the fluorine to foam separators that were used in the shipping containers when they were shipping these products. And then finally, I would like to, this is my second example. I would like to talk about how we can use our instruments to analyze battery materials. So we have a full suite of instruments in-house that are geared toward battery materials characterization. We can analyze several aspects of batteries. We can, of course, analyze the chemistry of batteries to get information about the chemical structure and the purity of the components. We can also look at the morphology of batteries. So we can get morphological information, bulk composition. We can get microscopic structure and chemical heterogeneity. Another aspect of batteries that we can analyze in-house is the electronic properties. We can actually get band gap information, electronic structure, and work function of battery materials. And then finally, in-house, we have sample handling mechanisms. Of course, a lot of battery materials are sensitive to air, lithium being one of the classic ones that is sensitive to air exposure. So oftentimes we will have these samples in a glove box, and then from the glove box, we will load them into one of our transfer vessels where they can be transferred in the inert environment to our instruments without breaking vacuum or exposing them to air. We also have in situ heating and cooling capabilities. We have an in situ for contact holder where we can conduct polarization studies. And we can also, as I mentioned, transfer to and from a glove box. So here's an example of some of the data that we have collected on battery materials. So this is XPS and Auger analysis on a battery after charge discharge. So you can see in this SEM image, we have graphite whiskers. This is a graphitic foam with an open frame structure. And we have graphite whiskers in the foam with large spaces in between them. We zoomed in on just one of these whisker features, and you can see these are the Auger elemental maps from the whisker features. And we can see the charged cathode has a pretty uniform distribution of aluminum and chlorine on the surface. Compared to after discharging on the cathode, we now see very little aluminum or chlorine on the surface. And that can indicate intercalated species on these graphitic cathodes before and after discharge. And then you can see on the bottom the XPS results before and after discharge, and on the pristine battery. We can tell on the carbon 1s that there is this shoulder on the peak on the fully charged sample, and that's due to electrochemical oxidation of this graphitic carbon. And then we have the aluminum XPS map. So we have a chloroaluminate intercalation that was evident from the peak position on the chlorine species. We can also see that the fully discharged has lower amounts of aluminum compared to the fully charged, which also corresponds to what we were seeing in the Auger maps. And then again, in the chlorine maps, we have a lower level of chlorine in the fully discharged compared to the fully charged, which again correlates as well to the Auger maps. This is an example of some TOPSIMS data that we have collected on a battery material. So this is LTO, LMO, and LTO NMC systems that have fast charging capabilities, but manganese dissolution can lead to reduced capacities. So here they were looking at the manganese distribution on the first cycle versus the 100th cycle, and we can see in TOPSIMS, because we collect a full mass spectrum at every pixel and we can collect a depth profile, we can then reconstruct some 3D maps to really look at the distribution of manganese as a function of depth. We can also, with TOPSIMS, get some molecular information, so we can see this organic lithium-containing molecule and how it's distributed on the surface before and after discharge. Another advantage of TOPSIMS is that we have trace level sensitivity, and that can enable detection of metallic species and show diffusion through the electrolyte. And then this is my last slide on battery materials. This is showing how we can use Auger electron spectroscopy to map with high spatial resolution LiPon versus lithium cobalt oxide. So we can see some chemical state differences in Auger that allows us to differentiate lithium in this chemical state versus lithium in this chemical state. And then we can also depth profile these materials to get depth information. We get the LiPon layer, lithium as a phosphate here in this top layer. And then as we go deeper into the material, we start to see some chemical differences where we see the cobalt come up. And then finally, we get into the platinum, titanium, and glass substrate. So these are examples of how XPS and Auger and TOPSIMS can help characterize battery materials. And then finally, just have a couple minutes left to show some quick additive manufacturing examples and how we can use surface analysis to help characterize 3D printed objects. So my first example is on a titanium alloy that is used for device implants. So the way these are 3D printed is they are used laser powder bed fusion. And I wanted to show how Auger can be used to analyze the final product that was made after 3D printing. So titanium is highly regarded as biocompatible. If you add some of these additives, you can get a material that's closer to the modulus match of natural bone. However, when you add these additives, the question then becomes, what does it do to the biocompatibility? So this is Auger electron spectroscopy analysis of the fresh surface. This is the SEM image and then a depth profile of the fresh surface. And then they immersed this 3D printed object into a human-like phosphate buffer solution at the pH and temperature that you would see in a human body, and they did this for 36 hours. So they wanted to compare the surface of the freshly printed device versus after it had been exposed to a human body-like conditions. And we can see in the fresh surface, we have this nice oxide layer forming at the surface. And this is a passive oxide layer that serves as a protective layer that is critical for biocompatibility. So you want this nice oxide layer for it to be biocompatible. And then if we look at the phosphate buffer solution, we can see that there's still an oxide layer remaining, which tells us that it is a biocompatible device that has been 3D printed. And then finally, very quickly, this is my last example. This is of cold spray deposition. So as the name implies, these are metallic particles that impact a substrate and form a deposit layer without melting. This can give us very thick layers that form. This is a 15 millimeter layer. One of the challenges faced by cold spray deposition is poor adhesion of the sprayed particles to the substrate. So in this example, they used Auger electron spectroscopy to look at the substrate and the deposit layer. So they have cold sprayed the copper deposit and then pulled it apart. And now they're looking at the substrate pulled apart face and the deposit pulled apart face. And they can see that there's some correlation. They're inversely correlated. Low copper on the substrate corresponds to high copper on the deposit. The really interesting thing here was the oxygen map, where you can see there is low oxygen on the crater edge versus the crater center. And that allows the metal of the particle and substrate to bond to each other adequately. So they were using Auger to look at the distribution of oxygen to try to determine if it was going to be a good bonding situation or a poor bonding situation of the cold sprayed copper onto aluminum. So in conclusion, I hope I have convinced you that surface analysis is important. I would like to make a plug that we have contract analytical services in-house. If you are interested in any of the analytical techniques I've shown in this presentation and would like to hear more, you can contact us by emailing analysis@phi.com, and we would be happy to provide you with a quote for our analytical services and discuss more in detail some of the surface analytical techniques that we could provide. With that, I would like to thank you for your attention, and I would be happy to take any questions.
Hi, Ashley. Thanks for the great presentation and insights into this. We do have time for a few questions. Let's start off with, how do your instruments handle insulating samples versus conductive samples?
Sure, yeah. So we have several different charge compensation techniques on our instruments. I would say that XPS is a very versatile technique. It can analyze insulating materials pretty well. Conductive materials are no problem for any of our instruments. If they're insulating, we have several different charge compensation techniques for XPS. Auger is a little harder to get signal on insulators, but we do have some techniques that we can use for that. And then TOF-SIMS also has charge compensation on it. So depending on the insulator, it could be possible, especially with XPS.
Great. And can you analyze liquids?
No, so all of our instruments are in a high vacuum environment, ultra high vacuum. So we do have to have samples that are compatible with an ultra high vacuum environment. Even samples that are very porous and outgassing could take a long time to pump down in our instruments. So the samples do have to be solid materials.
And we got time for one more. We'll slip in here. Are there any special sample handling procedures to be aware of?
Yeah, so because our instruments are so surface sensitive, we want to minimize the amount of handling that goes into them. This includes being very careful to handle any surfaces with gloves. Just the oils on your fingers or the salt from your skin can transfer easily to any sample surface. And because we're getting information from the top few nanometers, that can basically mask whatever feature of interest you're wanting to look at. So I would say if you are interested in sending us samples, we always tell our customers to try to wrap them in aluminum foil to minimize any chemical damage that could be done by sample handling.
Well, thank you again for the presentation. You can reach out, like Ashley said, to analysis@phi.com for any contract analytical services you need.
Thank you.
You can find more Lunch and Learns, plus the MFG Radio Network's other podcasts on Apple Music, Spotify, Google Podcast, or on our websites at todaysmedicaldevelopments.com, aerospacemanufacturinganddesign.com, and evdesignandmanufacturing.com.